Let's determine the enthalpy change for the thermite reaction using Hess's law and understand why everything is balanced the way it is. This is the thermite reaction where aluminum reduces manganese dioxide to produce aluminum oxide and manganese metal. We need to find the enthalpy change for this reaction. First, let's understand the principle behind Hess's law. Hess's law states that the total enthalpy change for a reaction is independent of the pathway taken, depending only on initial and final states. Whether we go directly from reactants to products or take an indirect pathway through intermediate steps, the total enthalpy change remains the same. To use Hess's law, we need the standard enthalpies of formation for our compounds. The standard enthalpy of formation for aluminum oxide is negative 1,676 kilojoules per mole. The standard enthalpy of formation for manganese dioxide is negative 520 kilojoules per mole. Aluminum is an element in its standard state, so its enthalpy of formation is 0. Similarly, manganese, in its elemental form, has an enthalpy of formation of 0. Now let's draw the Hess cycle to visualize the energy pathways. Our Hess cycle has 3 levels: the reactants at the top, the elements in their standard states at the bottom left, and the products at the bottom right. We have 3 arrows: delta H1 going down, representing decomposition of reactants to elements, delta H2 going right, representing formation of products from elements, and delta H reaction going diagonally, representing the direct reaction pathway. Let's understand why everything is balanced the way it is. To break down manganese dioxide into elements, we reverse its formation reaction, which changes the sign of its enthalpy. We need 3 moles of manganese dioxide, so we multiply the decomposition by 3. Delta H1 equals negative 3 times the formation enthalpy of manganese dioxide, which equals negative 3 times negative 520, giving us positive 1,560 kilojoules. Since aluminum is already in its elemental form, there's no enthalpy change for this component. Now let's calculate the enthalpy for forming our products from elements. We form 2 moles of aluminum oxide from 4 moles of aluminum and 3 moles of oxygen. Delta H2 equals 2 times the formation enthalpy of aluminum oxide, which equals 2 times negative 1676, giving us negative 3,352 kilojoules. Manganese remains in its elemental form, contributing 0 enthalpy change. Now we apply Hess's law to find the overall reaction enthalpy. According to Hess's law, the reaction enthalpy equals delta H1 plus delta H2. We have delta H1 equals positive 1,560 kilojoules, and delta H2 equals negative 3,352 kilojoules. Adding these together, 1560 plus negative 3,352 equals negative 1,792 kilojoules. Let's interpret what this result means. The negative enthalpy change means this reaction is exothermic, releasing energy to the surroundings. The reaction releases 1,792 kilojoules of energy, which is why the thermite reaction produces intense heat. This large energy release explains why the thermite reaction is used for welding railroad tracks and other industrial applications. Let's summarize the key steps in using Hess's law. First, we decompose the reactants to their elemental forms, reversing formation reactions. Second, we form the products from these elements using formation reactions. Third, we add all the enthalpy changes to get the overall reaction enthalpy. Our final answer is that the enthalpy change for this thermite reaction is negative 1,792 kilojoules, indicating a highly exothermic process.